Good morning everyone and welcome back to the new video, and in this video we will cover the volatility estimation of volatility, how to estimate volatility, and how to define correlation between variable. So let's start without any delay. So we are on chapter, wait a minute, where I am, 20, that is estimation of volatility. So for risk management we don't use implied volatility, right? We use volatility, simple historical volatility, and how to estimate it from a historical data. That is our goal. So we use time series modeling or statistical measure to estimate the volatility. We use time series models or statistics to measure volatility. So what are the models we use? So first model is simple volatility model that we have seen earlier. Volatility model. Volatility models. Second is our arch model, autoregressive coherence, autoregressive conditional heteroscopy models. Arch model. Second is Gauch model, generalized auto-regressive conditional heteroscopy model, and exponential moving average model. Sorry. So for this we only need asset or what we say unit price, right? Market variable. So market variable could be anything: stock price, asset price, rebate rate, anything. So we will consider market variable UI, U, and there and dates. Let's say from we took 500 date and market variable is UI 500, 500, 0. Time series modeling is a modeling where we work on time series data where date is involved, and we use rag operator very much. Rag operator is the shift operator in Python. That means if you are at I, so I plus 1 is rag of I, and to find the what we say percentage change, they in Python there is percentage change a function which can do this, that is UI equal to log form of SI, the current time stamp divided by previous time stamp, that is rag of SI. So you can think as a log of rag of SI, and rag operator is used very much. So if we have to find the volatility by the rag operator, the formula is 1 upon m minus 1 summation of till m I equal to 1 and un minus I minus mean of ui. So if ui is the rag, right? If we solve this equation we get the variance rate, and this is called variance rate, and m is the timestamp we are using, right? If we are taking 500 day, then m equal to 500. Okay, and to make it the formula simple, if we take very small timestamp or we consider mean equal to 0, this is mean of stock price, mean equal to 0, and we replace m minus 1 by simply m, and also we take percentage change, that is ui equal to Si minus Si plus 1 minus 1 upon Si minus 1. That is percentage change. then this formula can be reduced to this. U square n minus 1. So if we have a time series data, and this is the simplified formula, and if we have a time series data, the effect of predicting the next timestamp or predicting, we are on n, this is n plus 1, the n will have a greater effect than rest of time series. This effect might be less. It is auto regressive, the effect of every variable with itself, and the variable that is near to today has a more auto regressive value, ACF plot. So to understand this, you have to have a basic understanding of statistics. If I have some ACF PCF, I can show it. I made a project on it, if you like. How time series modeling works. It is not the predicting volatility. I predicted the unemployment rate, USA unemployment rate by Salima, the seasonality. Okay. Which one is? So you will get a better understanding how to do time series modeling. Okay. So we got CSV data of time series modeling, and you can see the column here. We just plot it, and to understand data, we should plot it. If we have a spot price, we just plot it. You should plot it, okay? And feature extraction, it is not important to see. That is a statistical test. Seasonal decompose. We find there is a trend of seasonality in the data, but you can see there is a trend in data. But in stock price, there should not be any trend. It should be seasonally decomposed. That means no trend, no seasonality. Simple, you can understand it. Okay. So to find there is a seasonality or not, then there is a statistical then auto differ stat ATF test. That if p value is 0.05, between less than 0.05, then it is not seasonal. It is seasonal. If it is above 0.05, it is not seasonal. And ACF auto correlation. That I want to show you. See, the autocorrelation is decreasing, is in decreasing rate. That means that the value that is near the net, the value that is near the net have a more autocorrelation, so should give a more weight to it. We have to give more weight, and that's how you do time series modeling. We just brought that is ARIMA model, autocorrelation moving average model, and that we will see a form of it that is exponential moving average model. Arima forecast, the forecast of Arima was not good. Okay, so let's go back to our topic. So we got that we should assign more weight to the near lag value. So we will assign a weight alpha such that summation of all alpha equal to 1, and the new formula would be weighted alpha of un minus 1. Yeah, just simple text. And there is a wrong term. To make a model more robust, we can see that wrong term mean. And what we mean by wrong term, if I have any, I have some on wrong term mean. App, where it is notebook IBNB. So let me tell you what is long term mean. If the our process is moving with constant speed or constant drift, then we can plot a line to it that can follow it till now. It is a long term mean. The mean of uh, this is our plot, and it is going like this. So our long term would mean will follow the process, and it is average, the longest average of our process, that would be this, because the it is mean reverting. So we will add a long term mean to it, right? Say our process have 100 variable, okay, and every variable mean, maximum variable mean is 30. So our long term mean is 30. Okay, so we will add a term long term mean plus to our weighted process, and this is arch model, and we will chat GPT more for arch model. Array, we don't want decision tree model. Arch model. There is a long term mean. This is the long term mean. AO is our long term mean, and alpha 1 is weighted, and epsilon t is our lag value. See, RT is a return of time, U is a mean return, RT mean return, and our drift term, this is will be the drift term or stochastic term. I think I am confusing you more. If return extreme, if previous value of the large value, then our variance will increase because of there is more weight. I think I am confusing you. Arch model is the model with weighted volatility plus long term mean, and here we are considering volatility, but instead that that correct term should be variance rate. Variance rate, okay, long term variance rate. And let's see exponential moving average model. So we have alpha I plus 1 equal to lambda alpha I, and that is our weight value. Lambda is our weight value. Exponential moving average. So the value of past data is decreasing, and the new data is exponentially growing. The average is growing with respect to change in stock price. That is exponential moving average model, and its model is final model is sigma variance rate, where 1 minus is lambda rate, m I equal to 1 lambda lambda I minus 1 u square n minus I plus lambda m sigma square n minus m. So in this you can see that we are using the volatility of past term too. So in exponential moving average, there is not the just stock price. We are also putting the volatility of present to predict future. And in this, we have weight and NMM. Let me clear it. What is N? And N is the volatility of nth day. Nth day. And M is our observed data. And in this way, exponential moving average work. If u square n minus 1, right, has a large value, then the price will go up because the weighted given to it exponentially. And if it is low, then the price will go down. You have to understand that. And to that, we have to decide the good amount of lambda. More lambda, the okay. Lambda is highly sensitive value, and if lambda would have high value, then the estimate will not based on part or moving average. If there is a more lambda, then it will be more stochastic, and the lambda value would not based on for the mean, long term mean, because exponential moving average is a mean reverting model where all the process revert around mean. In it, this is true in case of volatility, because sometimes volatility are always between some bound, and it is fluctuating between that. So if lambda is too small, 30, then it will follow mean very much. So it will be more stochastic, and that would be more right. And if lambda is too big, then it will not follow at all the mean. So we have to decide the a correct amount of lambda, so that a process is not so mean reverting, and on the same hand it is little bit mean reverting, and that lambda value is 0.94. That is given by JP Morgan in 1994, and where the 25-day M value is 25-day. Yeah. And let's see Gauss model. So Gauss model, G stand for generalized autoregressive, A stand for autoregressive, AR stand for autoregressive, and conditional heteroscopy. Okay, and its formula is simple. We have some rate of long-term mean with long-term variance with some rate of stock price, lag value of stock price, and some weight with our previous variance. And this is our Gauss model, Gauss 101 model, where alpha plus beta and gamma equal to 1, because they are all weight and their value should be 1. And for generalized Gauss 101, we use gamma equal to 0, alpha equal to 1, and alpha equal to 1 minus lambda, and beta equal to lambda. So in reality, we have to find the value of lambda where we have a maximized result. That is our Gauss model. And a more generalized Gauch model would be Gauch P and Q, where P is observation of US, observation, most recent observation of U2, and Q is most recent estimate of variance rate. Q is estimate. Estimate of variance rate. Q is most recent observation. How much p value we have to, how much we p value we have to, how much p value we have to choose, how much lag value we have to choose, and Q is the recent estimate of variance rate. Okay, and the generalized, if omega equal to long term mean, then our Gauch model is it's just a renaming, nothing fancy. Alpha u n minus 1 square plus beta to n minus 1. Okay, and I have to show this, and it is important. If this term, so for a Gauch model, this is our arch term and this is a Gauch term, and alpha is greater than ensure that possibility, and the alpha 1, that is first weight, alpha weight is impact of yesterday, and beta is the present past variance rate, that is this. And PQ, Gauch, generalized Gauch PQ, and if the value of stock price gives what we say, instead of stock price we use this term, right? Market variable, right? Let's say it is stock price is larger than the arch bump is more, and if variance term is forward is large, then the Gauch term have a more value and create a volatility presence, more fluctuation. Together we capture the volatility clustering and long term dependence to arch model, and how to estimate it by maximum likelihood on historical data. That is a statistical term where we put a random value and we find to optimize this, and where the probability is maximum. Just that. Okay. And yeah, the weights. I told you beta is a decay rate. Here it is. Beta is our decay rate. Okay. So if bk is 0.9, that on so it means that only 90% attendance is given to previous market variable. And yeah, apart from that, mean reverting process. Gauch is also a mean reverting process. That means the process revert around mean. Arch is also mean reverting process. Exponential moving average is also mean reverting. That is drift term. This is our drift term. Sorry, diffusion term, or Brownian motion, you can say, if we have it is stochastic differential equation, that for a long term mean, where BR is a long term mean. If it is 30 minus B, you get the idea. You have to visualize how the process might go, and where, yeah, A equal to 1 minus alpha minus beta. Okay, and how to choose between the models. So in simple, Gauch model is more robust because of long-term dependency and arch bumps, and because of mean reverting also. And theoretically, Gauch is more opening than exponential moving average. So we use generalized gauge model and how to estimate the parameter. A term statistical to maximum likelihood. So it's simple. Okay. I told you a parameter which increase the maximize the probability. That's it. So it is the parameter which have maximum likelihood that the object probability would be more, and that is maximum likelihood parameter. So for the goal, let's see, you have a data and a family probability model. Okay, maximum least, okay, likelihood estimation, find the parameter value that make the observed data likely possible under that model. So we have a condition and we have to find the parameter that will increase the probability of that goal or condition. So what is likelihood, right? We the concept of hypothesis testing is there. We uh, create a hypothesis where that data is normal distributed and give a specific u and sigma parameter, and we try to find how probable is the data I actually saw, how much probability is there that actually exit in that distribution, and then if it exit we find optimization technique or find the more value that can increase the probability of that occurring. So we assume R as independent normal variable with mu, and it is a normal distribution. That's my normal distribution formula, and then we find the integration, that is products, and that is this likelihood estimation is this. We get the variable of we input mean and variance of that type with maximum probability, and right, we do summation, take a partial derivative. That is a complex stuff, I don't want to work it. So you got the idea. We are finding the parameter parameter that gives a most probability of happening, most probability of variance rate. That's the maximum parameter. Yeah, and we saw our formula, that is 2 pi v exponents of minus u1 I. So for a simple, let's say probability of price decline. Probability of price decline is P. The probability that the particular stock decline. So we have 10 observation, and the probability of stock declining is actually 1. So one out of 10 observation, the price has declined. So our probability is 0.1, right? So other 9 probability do not is 1 minus P9. The particular probability of decline price and other 9 do not is. So the probability of other 9 that doesn't go down, price declining, is probability raised to 1 minus P raised to 9, and that's our maximum likelihood. See, we have a dot product in probability of all, and then we solve it. It go as exponential. Okay. So estimate. So we find p equal to 0, 1. That's so the maximum likelihood estimation is 0.1. I hope you understand it. And likelihood observation for another one is product of 2 pi v exponential of minus u I square upon 2v, and v is the value of maximum expression. Here V is value of maximum expression. So yeah, if we generalize it, we reduce it, then we come to different maximum hood parameter, that is 1 upon m I minus 0 m and ui. That is our condition. We have to maximize this. We have to maximize this. So we will find that parameter that maximize this. And how to consider maximum para hood. And our parameter is this, right? We have to maximize this ui upon vi. So our goal is to maximize this. And let me show you. So we have this table in our book, and you can see that the whole objective of this table is to maximize this value. So we will choose alpha, beta and omega such that we maximize our estimation. That is our maximum likelihood estimator, that is negative of log vi minus ui square upon vi. So we will follow iterative process. And another way to estimate volatility is we choose vl equal to sample volatility, sample variance, and then calculate the value variance, and with alpha and beta random parameter, okay, such that omega equals to vl upon 1 minus alpha minus beta, and 2 of parameter is estimated from historical data. And in this way we can do that. And for exponential moving average, we can estimate our objective function is negative of log vi minus ui square upon vi and upon omega I equal to 1, right? And so the value of lambda such that this estimator value will be maximum, that is our 0.9182, and in this way we can do that. And let's see, it's Gauch a good model. Okay, so Gauch is auto correlation model, right? So you can see it here. The Gauch model variety with passes of time. We know that during some volatility is high, during some it is low, and if u1 is high, then tendency of u1 the lambda value, the weight will be high. If u2 is low, then the weight will be high. And so we are here to determine how much the lag value have an effect on our current value, and that's we are testing in done by considering autocorrelation structure between this variable, and so very little autocorrelation. So the autocorrelation structure is this. For you can see there is stock price has autocorrelation, and for autocorrelation between this it is very low. Okay, so that's what they are saying. uh, First column show the lag considered with autocorrelation calculator. The second show the autocorrelation for ui. The third show the ui square autocorrelation. And the Koch model appear have done a good job estimating the data. For to test it, we use wrong box statistics test to find the autocorrelation between this, and that is given by this formula, where n k is autocorrelation for a rack value, and wk is, what is wk? Wk क्या है? I think there is a printing mistake. It should be nk. Yeah, and m plus 2 minus m minus k, and k value is 5. Okay, now we are using guard for how to forecast it. It's simple. Let me show you on board. At the variance rate at the end of n minus 1, this is our Gauge formula, wrong term variance rate, our Gauge term, arch term, right? And then so we can also write it in this term if we expand our arch term, and after expanding our arch term, okay, and after rearranging sum and find this, the final value is this. That is our, ये क्या बोलते हैं, Gauge model. So we have to find the expectation such that long term mean plus alpha beta gamma raised to t equal to square sigma square and minus vr. And in this way, so we will set our the equation for the n available in n minus 10, okay, f plus 1, so that so in MO model we had alpha plus beta equal to 1, that and if alpha plus beta is less than 1, then the final term of equation becomes progressively smaller. The term becomes smaller. If it is bigger, it becomes more, have a more value. But in our gas term, we have a wrong term mean, and for that we have a reversion rate, how the team decrease. That is 1 minus alpha minus beta for forecasting, and rest is same. So you can see that the variance rate decrease as the wrong time increase. The expected path for a variance rate with the current variance rate is about wrong term team. If our variance rate is about wrong term, then it will go to decrease. If it's zero, it will go to increase. That is logical because it follows the wrong term mean. And yeah, that's what how we do it. And you can solve it by putting the value in our formula, and you can find our wrong term mean, right? So let's see volatility structure, and the final formula for volatility average variance rate, for you can keep as an option, for option also, is VL plus 1 minus EAT, where A equal to log of 1 upon alpha plus beta, and VO minus VL, and that is similar. Okay, and yeah, let's discuss correlation. So we know the correlation is how data is correlated. We discussed this in earlier. So we have a covariance matrix. For correlation is derived from this formula. The correlation between two x and y is divided by covariance of x and y and sigma and y. So to find the covariance between this, we have formula expectation of x minus ux and y minus uy, where this is the mean of x and y. In this way, we can also derive it with the percentage change si equal to si minus 1 xi minus 1 y equal to yi minus yi minus 1 1 yi, and this is given x and n daily volatility of x term till n, estimated for n sigma yn daily volatility of y estimated in and covariance of n, and then we can generalize this as a covariance matrix of sigma both sigma here yn, and if we solve it, we know from earlier that our value is this. So we can simply tell that covariance, we can find the covariance by this formula. Simple. And this way we find the matrix that is 1 on every, and or we can say it is, and we have covariance here x y x1 y1, and that's how we find it covariance matrix, and its formula is w transpose omega w equal to 0, and that is positive semi definite matrix. Okay, and omega is where variance is expressed into v1 x1 plus w2 x2 and such that it I, and it cannot be negative because it's positive semi. Yeah, that's the summary of the chapter. I hope you like this chapter, and I try to make this chapter with lot of research and a lot of effort. Thank you for watching it, and I will improve my quality of video. I have many plans for this YouTube video, and I hope you show me support and it helps you in your con journey. That's all I wanted. Bye. Thank you for watching.